All right. So anyway, I would show my class how to type this into their notes. Well, I had a Spanish teacher come to me and was upset with me because some of my calculus students were in Spanish class and were taking a vocab test, and they had their Spanish vocab words typed into their calculators, evidently. And we're cheating. Exactly, Dan. You say that louder. Yeah. Exactly. And she was mad at me for showing them how to type these in, that they were cheating on her test. And I said, why are you letting them use a calculator on their Spanish vocab? So anyway, I said, I think you should maybe change your testing protocol, and I'm still going to show them how to use it. Now, I did tell my class, hey, just quit cheating. You're making me look bad here. But it's not funny. So anyway. So any issues? What was 15? What was the one I noticed a few people either didn't get to or fell asleep during, or was that 15? Yeah. I mean, you're going to have to do. You're going to have to do it. Can we do 15? Does it really matter if we go through one real quick? Okay. So 15 said y prime equals y squared, y of 0 equals 1. It says, now, I could give this in a variety of ways, okay? You're always going to have the difference equation and an initial condition, all right? So you're going to have that. And then they're going to want to know y of something, right? Now, in this one, they tell you pretty much everything. I mean, they say, use Euler's method, 4 steps, step size 0.2, estimate 0.8. I mean, they give it all to you. Okay, I might just say, use 4 steps to find y of 0.8. And then in that case, you're going to have to go, okay, 0.8 minus 0 divided by 4 is 0.2. You'll have to find the step size, the delta x, okay? But they tell you that it's 0.2. But it all should match up, right? So chances are, the only thing that could be different is I don't tell you the step size, I just tell you where you want to end up, because that's what we're interested in. What we're trying to do is not solve the differential equation necessarily for all values, but we're trying to find another value of the original function. So remember, solving a differential equation is finding the original function. And the reason you would want to find the original function, so you could find values on that original function. For example, we did Newton's law of cooling. The reason for solving Newton's law of cooling is we would get an equation for the temperature of the coffee. And then we might want to know what is y of 10. What is the temperature at 10 minutes? What's y of 12? What's the temperature at 12 minutes, right? That's the point of solving it, so you can find values on it. So Euler's method is a way to just find another value. You're given an initial value to find another value on the original function, but you're not solving the whole thing, right? Because it's just not solvable for us, at least now. So this is a way of approximating, much like we do that when we have an integral where we can't do the antiderivative. It's not solvable by the fundamental theorem, so we approximate it by 20 left rectangles, right? Or whatever. So that's the connection here, all right? So we have a difference equation that for us is not solvable, so we can't find any y values on the original function. Well, Euler's method will let us find some, okay, by going through this process. Okay, but it's an approximation. And again, if I ask you on the quiz, why is Euler's method not exact? Why is Euler's method an approximation? What would be a sentence or two that would tell why this is an approximation? It assumes a slope remains constant over the interval 0.2 in this case, right? Right? Because what are we going to do? We're going to come into here, and we're going to, well, here's what I would do on this one. I would say I'm starting at 0, Then I'm going to go 0.2. So I told you this yesterday. This is how I would fill out an Euler's method right here. As soon as I know the step size is 0.2, I would go to my starting position and I would fill in all the way down to my ending position, just like that. Okay? Then, of course, we know this is 1. So y prime, we're going to go over here. We're going to do 1 squared. We get 1. So right here, this is the key to Euler's method. This is why it's an approximation. What Harish said would be a great answer. Because Euler's method assumes that the graph of y is going to keep a slope of 1 for an entire step of 0.2 over. When in reality, it's not going to have a slope of 1 that whole time. It only has a slope of 1 at the point 0, 1. Right? But Euler's method assumes it stays that same slope the whole way, much like a left rectangle assumes the graph stays horizontal for 1 whole width. Or a trapezoid assumes it's linear for 1 whole width, when in reality the curve probably does not do that. So that's why those are off. This is why Euler's method will be off. Okay, how did we do delta y, or the rise? How did we calculate? This was the key column, I think, right here. It's easy to know how to get y prime because you just got to do that. Now, you guys are going to have to remember the table. I mean, it's not very hard. You got your point, you got to get your slope, and then what do you do right here? So slope times step size. Slope times step size, right? So it's this column times your step size. Slope times your run gives you rise. Slope times run gives you rise. That's the key step. So we're going to take 1 times 0.2. That's going to be 0.2. So that means we go over 0.2. We're going to go up 0.2, which makes sense if the slope is 1. So our new y is going to be our old y plus our rise. So we're now up at 1.2. We're 0.2 over and we're 1.2 over. Okay, we're going to do our y prime. So we take our y and plug it into our calculation there, and that's going to be 1.44. Then we're going to take 1.44 times 0.2, which is what? 0.288. And then we're going to add that on. So that's going to be 1.488. Probably should keep quite a few decimal places in there. Again, you'll have your calculator. So I started to say, I was talking about the test mode, then I got off my Spanish story. So on the quiz, if I want to go ahead and ask you some question where I want you to calculate an M30 or a T50 or something, you'll need access to the area program. So we probably not. So we just probably won't do the test mode. Okay. If I want you to be able to do that. Okay. So anyway, this comes back to 1.488, and so we do a y prime. Okay. At some point, I would keep it on your calculator, but what do you get for? Have we got something here? Somebody had something. How much? 2.214. And the rise then is 0.4428. And so now we get 1 point what? Like that. Okay, and then that comes down here. I don't even know. How did we get it? Yeah, they didn't have these final values here. Okay, so 1.93 you said. Okay, and then what?
3.7.
And then 0.746. Yeah, 4, 5, 6, whatever. And then 2.6. Okay, and then and in here they have 6764, and that was what we wanted, right? 0.8 and 2.676. So y of 0.8 is that. Okay, then in part B, now this could be a separate problem, right? And on the quiz, these could be separate problems. It says show that the exact solution is 1 minus t to the negative 1. So that's your verify. So we got y prime equals y squared. And we're supposed to show that y equals 1 minus t to the negative 1 is a solution. So let's talk about, I kind of skipped over that yesterday. This is the verify. It could be on there. Kind of depends how long the thing is. That's kind of older stuff. it's good to be able to do. But so what you're going to put over here is you're going to put that in for y. So put y in and square it. Over here you're going to want y prime. Well, we do the derivative here, so that'd be -1, and then 1 minus t left alone to the -2, and then we got to kick out a -1. Sometimes we forget that. We kick out a -1 because that derivative of the inside is that -t. So that would end up being just 1 minus t to the -2. Oh, this would be pretty easy, actually. And now power to power you multiply, so that's just 1 minus t to the -2. And so we got to check. So that's the verify step, right? You take your differential equation, you take your proposed solution and plug it in. Remember, in algebra class, if x equals 4 is a solution, we want to plug a 4 back in to see if it works, right? So if this is going to be a solution, we want to plug that back into the differential equation and see if it works. So that's what that looks like. So on those other ones, again, same thing. That's the verify step. Okay? All right, so that was part B. And then explain why Euler's method doesn't provide a good estimate of y equals 0.8. Well, we talked about that, right? It's just the derivative. I mean, if you look at the derivative, it's y squared. So every time you move a little bit of y, you square that. So it changes, so that derivative is changing. The slope is changing pretty rapidly. Okay? Didn't you have one earlier where y prime was just constant? Right, on that one of those first problems, I mean, y prime was constant, so the slope was never changing. Well, if the slope doesn't change, then this is going to work exactly, right? It's going to work perfectly. That's just it. It's like you do a horizontal line, you do left rectangle. It's a perfect fit. So if you do one where the slope is constant, then you assume the slope stays constant over that time. Well, it actually does, and so that's a perfect fit, right? That's a perfect fit. So it's important. I think it's important to understand how this stuff is working, how it's connected. But again, a lot of what you have to do in the quiz is work through this too. So there'll be at least one where you have to go through a table of values like this. You're going to have to remember how that table works. Okay. Now, also let's go to the calculator. So let's look at 13. Let's do. I guess I didn't get a pad out. Well, we can do that one. Who's got one in their calculator right now? 13. Who's got something in 13 already in their calculator? Come on. Liars. Nobody? Wasn't the last one we did where you had someone in your calculator 13? Maybe. Oh yeah, you were putting in 9.
I had needs and cleared up.
So you didn't even do 13, is what you're saying?
I said I had dog lead.
Jason, why is 13 blank?
Right?
All right. Well, we'll give Harish another try at this.
I was great last week.
Okay.
I was totally great. It's not like
It will. No, I mean, yeah, you got, so again, tomorrow we got to be able to do this. We got to be able to get on there, and we got to be able to do, still not letting in?
let me try again.
Yeah.
Oh, there.
You're in.
Is
All right.
it
13. Why?
Everyone got that right?
Okay.
What?
Did I see?
No,
I
that's-
had password again.
You're reaching.
Oh.
Lunchtime nation.
All right.
Yeah, we're actually gonna play lunch. We should all do
Okay, go to your graph screen. Okay, so it's y prime equals y minus 2. Now, did we have? Yeah, 11. So 11 said 1 plus t minus y. You can't put in t though, right? You got to put in 1. Okay, yes, you got to put in x. Okay, so understand that it's got to, the y, whatever your output variable, has to match what you're doing here. So if you want to leave this y1, so we talked about yesterday, if you want to leave that y1, then you got to put y1 over here. Okay, if you want to delete the 1 and make it a y, that's fine, but whatever you have here has got to match over here. And then your input variable, a lot of times it's a t in the book, you got to put in x. And so if I give it to you with t, you've got to put in x. And you can just remind yourself of that because you can see it right here. Okay, so we got y minus 2, and then y of 0 equals 1. Okay, go ahead. And then we're supposed to do 10 steps of 0.1. Okay, and so where do we go? We have to go over here to the 3 dots and put in our 0.1. And to be honest, you don't have to worry about the window really a whole lot. As long as you can see it on there, but you know you want to trace. You know you're going to trace to or to 1, y of 1. So you can literally just trace to a 1. That's all you really need. Yeah, you can just type the 1 and enter, and that's the value you want. Okay, so that's negative 0.593. So we write that down. Now let's change the step size. It says the 0.05. So now we would do 20 steps. Now you might have to calculate the number of steps, right? I might say, or not the number of steps, but the step size to put in. Again, I might say, give you y of 0 equals 1. I'll say, use 20 steps to find y of 1. Okay, so you're going to go from 0 to 1 in 20 steps. So you're going to have to do 1 minus 0 divided by 20 to get your step size. So there it's a little different. So it was negative 0.593. This time it's negative 0.653. Now the graph looks almost identical. We don't really notice much difference, but the points are actually very different again because Euler's method is assuming different, a slope for a smaller amount. So we're getting more accurate. We're getting a better answer. Okay, so if I give you one of those, all you need is an answer, right? Negative 0.653. But understand what it is we're finding. That's the key. Yeah.
So in a differential equations class, we're working on solving these a lot.
Right.
When you're trying to solve them, is it like using this but then just incorporating a limit?
No, actually there's more techniques. So in other words, what we're saying right now, so when we talk about sine of x squared, there's no antiderivative. So we have to do an approximation technique. Now that is true. There literally is no antiderivative that we can't use fundamental theorem part 2. Now, there are a lot of other integrals, and I should go get one of these. I used to have one, and when Mrs. Larson was right next door, it was really easy. But the CRC handbook, I don't know if you've taken chemistry, I don't know if she ever even shows you that anymore. And so, we have to do that. But there's this thing called the CRC, these scientific handbooks full of formulas. The thing is this thing. I mean, it's just huge. And there'd be a section in there of integral formulas, 700 and some, a lot of integral formulas. And what they were was, if the function looks like this, then you do, then the antiderivative is this. And there would be variations off of ones, and they would be complicated, messy looking things. And so you would have to, and I did this when I was in college, and so you'd be looking at your integral, and you'd look at the makeup of it, or you might have to do some algebra to rearrange it, and then you had to match it to one in this big table of integrals. And then you would, and then they would tell you the antiderivative, then you could plug in your numbers. Okay, so there are a lot of functions where you would look at them and you'd like, I have no idea how to do the antiderivative. One of the things you learn in Calc 2 is some more antiderivative techniques, right? So kind of a long answer to your question here, but I'll get to it. So we have some that I could throw up here right now, some integrals, and you would not know how to do the antiderivatives, but there is an antiderivative, right? But if we didn't know how to do it, we would do an approximation technique. Same thing with differential equations. So when I say a differential equation, when I say y prime equals y squared is not solvable, it's not solvable for us right now. So we do Euler's method. Now, actually, in Chapter 7, we're going to learn how to do y prime equals y squared. We will actually be able to solve that. Okay, so what you spend most of your time doing in a differential equations course is learning how to solve the various types, right? So it's kind of like in algebra class, you learn, in 8th grade, even starting in 7th grade, you learn how to solve linear equations, right? Then you get into algebra 1 and you get into quadratic equations. Oh, there's a quadratic formula, there's factor, right? There's different methods for doing a quadratic. Exponential log equations, there's some techniques you can use. use trig. There's a lot of it are algebra techniques. But, so you learn techniques. That's what a differential equations course is like, is you identify, first you look at the difference equation, you identify y prime equals y squared is what's called a separable differential equations. And there's a way to solve it. There's one called, for some reason this name is so bizarre that I remember it from college. There's a differential equation called Wronskian. A Wronskian differential equation. And when you identify one as a Wronskian, this is what you do. You do these steps. And there's other types, Bernoulli differential equations. And then you do something else, you know what I mean? So you learn how to solve different types of differential equations, is mostly when you do that. But you also would probably do some approximating. Spend some time with like Euler's method and maybe that Runge-Kutta, that other method. Probably do some of that too. In the differential equations course, yeah. All right, so that's what we need to know for the Euler's method. Basically those two things. Be able to do it in your calculator and trace, be able, well, two things calculation-wise. Be able to go into your calculator and trace, and that's if you have 10 or more steps. And then if you have less than 10 steps, probably like 4, 5, 6, something like that, then we're going to do take. You've got to be able to do the same thing. And then maybe talk about Euler's method or explain like the answer for each gave us a little bit. Okay, so now the rest of the time here, I'm gonna give you a few problems you can work on. The sample 3-pack is something we'd like to kind of get done with. It's not like we're gonna turn it in when spring break's over, right? Like when you come back, so you have to be working on it. But it's something we should steadily be working on. So if you have some time, some extra time today, you can. Tomorrow when you're done with the quiz, that's what I'll tell the sub that you have, that you can do. So we want to be getting done with that. So anyway, remember over/under estimating, right? Those kind of things. What makes a left and right be over and under? What makes a trapezoid and midpoint be over and under? And then our formulas, which are going to be on the quiz for you. But finding the K1 value, the K2 value, and plugging those in. And then, or how many rectangles or how many trapezoids does it take to get within a certain amount to be able to use those. Okay, so that's pretty much it right there. Understanding that if you have single digits, right, if you have single digit subdivisions, less than 10, you might have to draw out some rectangles. You might have to, kind of like we did on the last quiz, draw out some rectangles, draw out some trapezoids, write out the sum, add it up on your calculator, get the calculation, be able to answer questions about over, under, the max error formulas, okay, we just said, and then Euler's method, less than 10 steps, write it out in your table, more than 10 steps, we trace it on our calculator. So, now, I've got down here a couple problems that you could look at and do as some kind of review. Now, 29 through 46, I believe, are those ones we already did. So I put those on there to look at it, just be able to do that. Let me double check that. I think those are the ones where we did the must be true, might be true. Yeah, that's the must be true, might be true, can't be true, that kind of thing. So we already did those, okay, in homework. So I'm just saying those might not be bad ones to look over again. And then in 6.2, this is where we have the error formula. So these are ones, I think these are ones we didn't do, I believe. And then 6.3, here's just a couple more with that Euler's method. So whatever you want. I'm going to come around and check on this, but 6.2, let me see. I think we maybe did 11, but I don't think we did 10 or 15 on 6.2. And on 6.3 we didn't do 10 or 12. So those would be ones, to kind of look at here. Wish we had some basketball, but I'm sorry. Yeah.
For Euler's method, if you do it on the calculator,
We just literally write out the answer.
Literally, you'll just put the, whatever the Y value is, so you'll trace, so what it'll say is, it'll say, again, you guys have to know, now, probably on the drawing, the trapezoids, if I say, I'll probably say draw a sketch or whatever. If I say compute an R4, okay, then you just know automatically, since it's 4, I have to write this out, right? If I say compute an R20, you just know automatically I can go to my area program, I can do R20 and just write down the answer, right? Same thing with Euler's method. If I won't say write it out, I won't say use your calculator, I'll just say use Euler's method with 4 steps to find y of 2. You have to do a table because it's 4 steps. If I say use 10 steps to find y of 2, then you literally go to your calculator and you just write y of 2 equals the answer. So yeah. So it's just an automatic that if it's this many steps, I have to write it out. If it's 10 or more, I don't. Okay.
If it's like 6 or 7 steps, do we have to write out all the steps, or can we go like capital 1 plus that 2 dot dot dot?
Yeah.
7?
Yeah, kind of like that one we had 10, and we did write it down here, down the trapezoid, where that's actually okay. I mean, if it's 4, you might as well write them out. But I see what you're saying. If it's 8 steps, 8 midpoint rectangles, do you have to write out all 8 F of? Probably not. Yeah, write it out. See, kind of what the pattern would be. I would be okay with that. Yeah, I'd be okay with that. Okay, so you use the rest of the time here to work on those, work on the sample 3. Okay.
That's the 11.